All right, so this is going to be another talk that uses the generalized or the Speckins notion of contextuality that we've just been hearing about. And it's a fairly basic point we're making about this definition of contextuality, which is shows that there's a fixed number of ontic states you have to use for any given system. It's going to turn out to be 4 for a qubit. And once you've fixed how you represent the states in the model, everything else is fixed automatically. So there's much less freedom than you might think. So I'm gonna try and give you a proof of this theorem, and then say a little bit about what you can do with it. All right. So I'm going to be using diagrams a lot in this talk, so I'm just going to dive straight in and explain what sort of diagrams I'm going to be using. So they're going to be diagrams where time goes from bottom to top. And if I draw something like this, I mean I'm applying some transformation F and some transformation G at the same time on 2 different systems, and then I'm applying H on the first system, for example. Okay, and some special types of transformations are going to be preparations. So there's no system that comes in, we prepare it somehow, and now we have a system coming out. And measurement effects, so we have a system coming in, we sort of destructively measure it, and then nothing comes out. Okay, and then I can wire these things together. So if I draw a diagram like this that has no wires coming in or out of it, then that just represents a probability. So if I draw a diagram like this, then I'm talking about the probability of seeing this particular measurement outcome E, given that I prepared the system according to P and transformed it according to T. Okay, so far this is just a kind of way of drawing things. It's basically just quantum circuits turned on their side. So I haven't really done much yet. The first sort of non-trivial thing I'm going to do is basically I'm gonna bake in the notion of noncontextuality. So we've already heard about this definition in 2 talks today, Konstantino's and Barbara's. So I'm going to be fairly quick. So the notion of noncontextuality is based on the idea of operational equivalence. So for example, I might have some measurement outcome E and another one E primed that give the same outcome, that give the same probability. Remember, when I close a diagram like this, it just means a probability. So E and E primed give the same probability on all possible preparations P. Then we say that E and E primed operationally equivalent. And what we do is actually just kind of bake this notion of operational equivalence into the pictures. So if E and E primed have this property that they give the same probability, then we just treat them as being equal. Okay, so E and E primed might involve doing very different things in the laboratory, but if they give the same statistics for all preparations, then for the purposes of these pictures that I draw, they're the same thing. Okay, so if you're thinking about quantum theory, a measurement outcome is equivalent if and only if it's represented by the same PAVM element. And so this is just saying that when I draw an effect like this, I'm really talking about the PAVM element. I'm not including any information about the context. Okay, so that's how we're going to deal with operational equivalences. So now I can talk about non-contextual models. And again, we're going to use the diagrammatic notation. And the diagrammatic notation is that we draw a blue box on something if we want to go from the operational description of it to how it's described in some underlying ontological model. Okay, so the thing inside the box is just your preparation procedure P. So in quantum theory, that would be a density matrix. But then once I've drawn this blue box around it, now I'm talking about the probability of some ontic state, given that we've prepared the system according to P. Okay, so we're imagining that the quantum system is actually represented by this underlying ontic state, and we draw this blue box to find out what the probability is. And another subtlety of this notation that might be quite hard to see is that we use thick lines for quantum systems and we use thin lines for ontic states. Okay, so drawing this box allows us to go from quantum systems to ontic states. Okay, so that's just a way of writing this probability. And this is automatically non-contextual because I said if P was equivalent to some other thing P primed, then we would treat that as being the same object in these diagrams. So this probability is only allowed to depend on the operational equivalence classes of the preparations, because that's what these pictures represent. So we can do the same thing for measurements. If I draw a blue box around the measurement, then I'm asking what's the probability of that measurement outcome given whatever ontic state is coming in here. And finally, for transformations, I can ask by drawing a blue box around a transformation, what's the probability of some output state lambda primed given an input state lambda and the transformation T. Okay, and just to emphasize again, we're talking about the operationally equivalence classes of transformations. So this is automatically transformation non-contextual, this is automatically measurement non-contextual, and this is automatically preparation non-contextual. Okay, and then one nice feature of this notation is that if I want to work out the probability, if I want to reproduce the probability I get operationally using my ontological model, I just put blue boxes around everything. And when ontic states are connected like this, it just means you integrate over them, okay? Because operationally, you never see the ontic states. So you just multiply up all the probabilities and integrate over them, okay? This is just the normal way of combining these probabilities to get the operational probabilities back. Okay, so now that I've set up my diagrams, I can actually start talking about the structure theorem. The first assumption we need is something called diagram preservation. So we think this is a sensible thing to require of an ontological model, but actually the instances of it that we require for the theorem are quite limited, so I'm only going to talk about those. The first one is very simple. It just says that the probability for getting some outcome E given a preparation P and T according to the ontological model is exactly the thing I did before, where we write the probability for the ontic state given the preparation, update it according to the transformation, do the probability for the effects, and then integrate over the ontic states. Okay, so this is totally standard. This is just a diagrammatic way of doing the normal ontological models framework. And then we can state the assumption that the ontological model reproduces the operational probabilities diagrammatically like this. Okay, so far we haven't really done anything. A slightly more controversial case that we're going to need is that if we look at the identity transformation at the operational level, so this is the transformation that doesn't do anything to any state. This is the identity channel in quantum theory. We're going to assume that the representation of that in the ontological model is the identity. Okay, so whatever ontic state comes in here, if we apply the identity channel to it, we get the same ontic state out. And this seems like a fairly natural thing to require, because one way you might have done this identity transformation is to just wait for 0 time to elapse and not allow anything to happen, in which case it's very natural to think that the ontic state shouldn't have changed. Okay, and by non-contextuality, that then has to be true for any other way of implementing the identity transformation. Okay, and then one more case we're going to need is that if we have a special type of transformation that's been implemented by performing a measurement and then perhaps conditional on the outcome of that measurement doing some new preparation. So there's no quantum system going from this input to this output. The only correlation is that the choice of how we re-prepare the system might depend on the measurement outcome we got when we measured the system. So this is like a measure and prepare channel. We're going to assume that that's represented in the same way in the ontological model. It's just represented by, given the input ontic state, working out the probabilities for the measurement outcomes, and then given that measurement outcome, using the usual probabilities for the new ontic state, given whatever preparation we did. Okay, so there's not allowed to be any sort of extra information in the ontic state here that comes out of the output of this channel, because everything has to go via the representation of the measurement and the preparation. And these assumptions are called diagram preservation because they're all of the form, if I draw a blue box around something, that's the same as drawing a blue box around its components, which is what diagram preservation means in general. Okay, so just writing these things in equations, the identity on the ontic states is kind of a direct delta that forces the new ontic state lambda prime to be equal to the input ontic state lambda. And this is saying that the probability for the new ontic state lambda primed, given some input state lambda, is just the probability for the measurement outcome given lambda times the probability of the new ontic state given the preparation. Okay. The second assumption we need is nothing to do with the ontological model. It's just a property of the operational theory. And that's a property called local tomography. You probably don't need to worry about this too much if you're not familiar with it. The idea is basically just that it's possible to do process tomography and work out what process you have in your operational theory just using product states and product measurements. Which is a property that's true in quantum theory and true in quite a lot of other theories that people think about. Okay, and actually for our purposes, it's useful to have an equivalent formulation of local tomography, which is that any transformation can be written as a linear combination of these prepare and measure transformations that I talked about. So this might look a little bit weird, but if you're used to the Choi-Jamalkowski isomorphism in quantum theory, then this is equivalent to the statement that any bipartite state in quantum theory can be written as a linear combination of product states. Okay? They can't be written as a convex combination, but they can be written as a linear combination. So these Rij's don't have to be positive numbers. Okay, so that's local tomography, and finally can actually get to our theorem, which is that the representation of any kind of transformation in a non-contextual ontological model satisfying our assumptions can just be found by using this map chi and its inverse chi to the -1. Okay, so that's a little bit confusing. So let me just spell out what this chi is. Well, one special case of this thing is if the transformation happens to be a preparation, in which case we don't have anything going on underneath. We just have this chi here. So that means that chi is just the map that takes some preparation and gives you the probability for the ontic state given that preparation. Okay, so we've just moved the blue box from being on top of P to being above P. So chi is really just this. Chi just tells you how to go from preparations in your operational theory to the representation of the preparations in the ontological model. And then, as I said at the start, once you've chosen this chi, you've fixed your representation for all transformations, because any other transformation just has to be represented by using chi and chi inverse. And in particular, because I've put chi inverse here, chi has to be invertible, which will be important later. Okay. It's a bit risky to try and do a proof in the last talk of the day, but I'm going to give it a go. It's mostly just playing around with some of these diagrams. So the first thing we do is use that equivalent formulation of local tomography that I talked about. By local tomography, we know we can re-express it as some linear combination of these measure and prepare transformations. The next step we use is it's a little bit subtle. So in an ontological model, convex combinations have to be preserved. So if what you've done operationally is toss a coin and decide whether to do preparation 1 or preparation 2, then in the ontological model, the probability of getting a particular ontic state should just be half what it was for the first preparation plus half what it was for the second preparation. This isn't a convex combination, but what we can do is we can say that since this blue box has to be a convex function, a convex linear function, it has a unique extension to a linear function. So what we're really talking about is that unique extension. Okay, so that allows us to use linearity to pull out these coefficients. And now I can use that diagram preservation assumption I showed you to split the representation of this measure and prepare channel into the representation of the measurement and the preparation. So that's the first step. The second step is to focus on what happens to the preparations, how they're represented. And again, we just argue that this thing has to be linear, and therefore we can just decide to represent it by some box that we put after the preparation pi. Okay, so this isn't necessarily a physical transformation that you could actually do in the laboratory. In fact, in general, it won't be. But it's still kind of a mathematically valid linear transformation on the system. So we can draw it as a box, even though it's not a box that we could actually build. So this is just kind of a notational step of rewriting this linear map that used to be drawn by doing boxes over something and rewriting it as doing this chi after the preparation. And now for effects, we can do the same argument to say that this is also just some linear map that takes us from the effects to the probability of the effects given the ontic states. So I'm going to call that linear map phi. Okay, so plugging what we've just done back into step 1, we have that the preparations are represented using this chi and the measurements are represented using this phi, which is, and then we can just use the fact that this sum in here equals t. So that's just by definition, this was a representation of t as a linear combination. So we can just put that back to being t. And now we're almost at what we want, except that we want chi and chi inverse here rather than these two arbitrary maps, chi and phi. Okay, so how do we do that? We use the last bit of diagram preservation that we haven't used yet, which was that the representation of the identity, which if I put the identity in here, is just going to be chi and phi after each other. We use that representation of that operational identity has to be identity at the ontological level. Okay, so that means that phi followed by chi is the identity. And now, if we just look at the probability of getting some measurement outcome E when we prepare some state P, that has to be reproduced in the ontological model, which is represented by the probability of some ontic state given P times the probability of some effect given the ontic state. But by definition, this first thing is just P followed by chi, and the second thing is just phi followed by E. So we have to have this equation. And this has to hold for all possible preparations and effects. which by local tomography means that this is the identity transformation in here, okay? Because certainly this would equal this if this was the identity transformation, and by local tomography, if it looks like the identity transformation on local preparations and effects, it must be the identity transformation. Okay, so now we've got that phi followed by chi as the identity and chi followed by phi as the identity. And so we've got that phi is the inverse to chi, which is exactly what we wanted. Okay, so that's how we prove our structure theorem. And in the remaining time, I'll just talk about a few ways that this can be used. So the first thing is something I mentioned at the start, which is that this constrains the number of ontic states. And the reason is just this invertibility that I just talked about. Okay, so that means that because chi is invertible, it's just a linear map on vector spaces. That means that the dimension of the input vector space has to be equal to the dimension of the output vector space. Otherwise, there's no hope for it to be invertible. The dimension of the input vector space is just the dimension of the state space in the operational theory. And the dimension of the output state space is just the dimension of probability distributions over the ontic states, which is just the number of ontic states. Okay, so the number of ontic states has to be equal to the dimension of the operational state space. So for example, a QDIT has a d squared dimensional state space, because we're talking about density matrices here. So they live in a d squared dimensional space, which means that they have to be represented using d squared ontic states. So for a qubit, d squared is 4, so we need 4 ontic states. And this is kind of surprising that you're only allowed to use 4, because it's been shown that actually any ontological model of a qubit needs an infinite number of ontic states. So if you just combine the fact that any ontological model needs an infinite number of ontic states with the fact that a non-contextual model must use 4 ontic states, you immediately have a proof of contextuality for a qubit. But it's not just useful for that. There's also people that have proposed ontological models for subtheories of quantum theory that still use more than 4 ontic states. I think this one used 8 ontic states. So we can immediately see that those models have to be contextual as well, okay, because any non-contextual model should have used 4. Okay. Another quite nice thing is that our argument never actually really used that the probabilities for the ontic states were positive. So if you're interested in things called quasi-probability representations, might also have heard of them under the name Wigner function. Those are also going to be constrained by our structure theorem, because they're basically the same as an ontological model, except that the probabilities don't have to be positive. Okay, and so in the language that people use in the quasi-probability literature, this means that you should always use a complete frame and not an over-complete frame to define your quasi-probabilities. And then one more application I'd like to mention is, so our theory applies to any locally tomographic theory. So that includes quantum theory, but it also includes just the stabilizer subtheory of quantum theory. Okay, so that's a subtheory that's used in quantum error correction and stuff like that, where the states are eigenstates of Pauli operators, transformations of Cliffords, etc. So we can apply our theorem to that and constrain what the non-contextual models of it look like using our structure theorem. And then once you've done that, once you've gone from the kind of the zoo of possible models you might have started with down to these ones that use exactly d squared ontic states and have this very constrained form, it's not too much more work to then for the particular case of the stabilizer subtheory to pin it down to a unique non-contextual model, which is one that's already in the literature. It was defined by Gross for odd dimensional systems. And in even dimensional systems, we show that you get so many constraints that there's no non-contextual model at all, which was something that was already known for qubits, but we've now generalized to all even dimensions. And yeah, just to emphasize that the structure theorem is really doing a lot of the work in this result, because it's kind of what you need to narrow things down enough to then use kind of more elementary techniques to finally pin it down to one possibility. And you can find this paper on the archive if you'd like more details. Okay, so just to very quickly conclude, non-contextual models, once you take into account transformations, have a surprisingly rigid structure, a fixed number of ontic states, and only being able to choose how you represent states, everything else being done automatically. If you violate this structure, you have to have contextuality. If you're looking for non-contextual models on a computer or something, you can use this structure to narrow down what you have to search for. And it was very useful in studying the non-contextual model of the stabilizer subtheory. Okay, thank you very much.
Nice. Let me make a question. I got the impression that you have just one chi. Is it true? Because you use some factorization like property in step 2. So the chi box would not depend on the transformation you were using before. Is that true?
Yeah, so it doesn't depend on the transformation. That's very important, because basically we're saying that the only freedom in defining the model is just to pick this chi. So if you could pick a different chi for different transformations, you wouldn't really have a constraint. So it doesn't depend on the transformation. One thing it does depend on that I've kind of glossed over here is the systems that the transformations act on. So really, there's a family of chi for each system. So for quantum theory, in each dimension, you need to define your chi. Okay, you need to define a chi for qubits, a chi for qubits, etc.
Okay, but given the system, you have just one possible,
Exactly.
and you can characterize it somehow. Okay, thank you.
Yeah, like in the case of the stabilizer subtheory, we were able to work out exactly what this chi has to be, for example.
Can I ask a question about this last point? So regarding this characterization of stabilizer subtheories, does that give you faster simulation algorithms using like a stabilizer rank decompositions or this non-contextual decomposition of VQE that we heard on the first day from Will Kirby?
It's not something I've thought a huge amount about, but as I mentioned, this is a model that's already been in the literature. It's Gross's discrete Wigner function, and that has been used to study simulations of stabilizer theory. You can even use it to simulate things that are outside of the stabilizer theory, but the computational cost kind of scales with the negativity. But this is kind of, I guess this is offering a justification for why you should start with that model in the first place.
But it doesn't really address the qubits, right? So it's not directly relevant to qubits, I guess, the characterization, right?
Yeah, so the qubits are always a bit of a mess in this literature, because there is no gross model for qubits. You can sort of define families of models, but there isn't a kind of unique nice one like there is in odd dimensions. And we're kind of also offering an explanation of that, in as much as the reason there isn't a nice one is because of the contextuality. Yes.
Okay, thanks.
May I ask a quick question?
Yeah.
Hi, this is Will Kirby. I'm trying to understand how the application of this to the quasi-probability representations, or how I should think about that. Because we can have a quasi-probability representation for the whole theory of quantum mechanics. So is the way to think about this result just that for a given dimension, the quasi-probability representation of that has to have only that dimension, like it can't have a higher dimension? How should I think about that part of the result?
Yeah, that's basically right. So the language would be something like that. The size of the phase space has to equal the dimension of the state space. Yeah, I think beyond that, when we're not really saying much new about the quasi-probability case, because I think people already knew that once in the language of quasi-probability representations, once you've defined a frame, in this case where you're using a minimal number of phase space points, then once you've defined a frame, that fixes your dual frame, which is kind of what this chi and chi inverse is getting at. So yeah, really I would say the new thing for quasi-probability representations is just that you shouldn't use a larger phase space.
Got it. Okay, thank you.